Alright, this video is going to cover Objective 5 in Chapter 2, which is kind of looking at the difference between atoms, ions, and isotopes. And so just to kind of review before we get into the difference, atoms are neutral. Remember that atoms are the smallest unit of matter. They make up everything. A single element is kind of like the smallest, or a single atom is like the smallest unit of an element. And atoms, remember, have the positive protons, the neutral neutrons, and the negative electrons. And so because atoms are neutral, we know that protons and electrons are the same. So anytime you see the word atom, we know that these two particles are equal, okay? We've also talked about valence electrons and how those are the ones that are on the outermost shell. And atoms want to have 8. I kind of mentioned before there was an exception, a couple exceptions. Your first couple of elements, hydrogen and helium, only have 1 or 2 electrons, so they only need 2 to be kind of happy. But every other element wants to have 8 valence electrons. And so what will happen is, if they don't have 8, they could possibly lose or gain electrons to kind of fulfill that 8 on their outermost shell. And so when that happens, if an atom loses an electron or if an atom gains electrons, they're not going to be neutral anymore, because then the protons and the electrons will have a different number. And so what happens is, when they lose or gain, we no longer call them an atom, we now call them an ion, because they now carry a charge. And so by definition, an ion is just a charged particle. Now, depending on what happens, that will determine whether it's a positive charged particle or a negative charged particle. And so our two different types are a cation and an anion. So cation and anion. And so if an electron is lost, we now have more protons, which are positive, and so therefore that gives it an overall positive charge. And if the atom gains electrons, then it now has more negatives than positives, and so it becomes a negatively charged ion. So once again, an ion is just a charged particle. So when atoms do not have a full outer shell, they will sometimes either gain or lose electrons. And then at that point, we no longer call them atoms, we now call them ions. If they're positive because they've lost electrons, it's a cation. If they're negative, it's because they gained electrons, and we call those an anion. So here's a couple examples. So sodium had 1 valence electron in its outer shell, and so honestly it's a lot easier to lose 1 than gain 7. And so when that ion, or when this electron gets lost and it goes somewhere else, now we have more protons in the middle, okay? Now over here's another example. And so this is what happens when these two guys bond, okay? Sodium and chlorine are what make salt together. And this is really why that happens, is sodium needed to lose 1. Well, chlorine over here has 7, so they just need to gain 1. And so normally sodium will just gladly let chlorine have that electron. And so when chlorine gains that electron, it now has more negatives, and so now it has an overall negative charge. So atoms are electrically, okay, remember anytime you call it an atom, doesn't matter what it is, carbon atom, sodium atom, oxygen atom, if it's an atom, the protons and electrons are the same, and therefore they are neutral. And if it's a positively charged particle or ion, it is known as a cation. A negatively charged particle would be an anion. All right, so kind of looking at these symbols, we can determine whether it's an atom, which is neutral, whether it's a cation, which has a positive charge, or whether it's an anion, which has a negative charge. So if you look at the first one, it pretty much just has the chemical symbol, and so that tells us that it is not charged, okay? And then on these other ones, they have a symbol or a sign along with a number. And so that tells us that this has a charge of -3, this one has a charge of +2, and this one has a charge of -1. So what happened here is this atom gained 3 electrons. This one lost 2 electrons, and here we have an extra electron as well. And so negative would be an anion, positive would be a cation, and no charge would be an atom. All right, so sometimes those chemical or those ionic charges will be on the periodic table. Once again, it depends on what periodic table you're looking at. And so always you will see the atomic number, which remember is just protons. You'll see the atomic mass, or sometimes the mass number. Okay, once again, it depends on what periodic table you're looking at. Or sometimes the chemical symbols, when they're written by themselves, like this over here, they will be identified by their mass number and not the atomic mass. And remember that the mass is always the protons and the neutrons together. And then sometimes you'll see that ionic charge. And so if that atom typically will form ions, then sometimes you'll see those charges written on the periodic table. And so here's a chemical symbol here. We've got boron. All right, and so we need to figure out what each one represents. Okay, so we've got 5. We have 11. And we have -3. All right, so this smaller whole number over here, the 5, that's going to be our atomic number, which is the number of protons. The 11 would be the mass. In this case, it would be the mass of this single atom. Remember that to find neutrons, we simply subtract. Okay, so we know that this one's the mass because it's bigger. And then over here, we have a negative symbol. So this is going to be the charge of our ion. Okay, in this case, it's an anion because it's negative. Once again, mass is protons plus neutrons, and the atomic number is just the number of protons. All right, so the next thing we need to talk about is this word here, isotopes. So we have atoms that are neutral. We have ions that are charged particles. And isotopes are atoms of the same element that have different masses. And the reason they have different masses is because they have different numbers of neutrons. So remember that the protons, that atomic number never changes for a particular element. Carbon is always 6. Oxygen is always 8. Hydrogen is always 1. Helium is always 2. Sodium is always 11, okay? The protons never change for a particular element. But the neutrons, those neutral particles, they can vary from atom to atom of a particular element. And so since they don't have a charge, they don't really affect anything other than the mass. So the protons and neutrons together determine the mass of an atom. And the mass number is usually written with the isotope. So here you have oxygen 16, oxygen 17, oxygen 18, and the number of protons, okay, in this case the blue, the number of protons is going to be the same in every picture. But what varies from atom to atom to atom are these neutrons. And so as we go through these oxygens, if there's 8 protons and 8 neutrons, that's a mass number of 16. 8 and 9 would give us 17. 8 and 10 would give us 18. So they're all oxygen because they all have 8 protons, but the individual masses of these will vary depending on the number of neutrons that they have. And so these are what we refer to as isotopes, okay? The number of neutrons doesn't change how it behaves or anything like that. It simply changes the mass for that particular atom. And so this right here is why we get an average on the periodic table. Not every atom has the exact same mass for that particular element, and so an average is calculated depending on the general percentages, and so that's how we get those decimals on the periodic table. Okay. All right, so let's kind of practice. We've done some of this already in a former video, but this time we're going to take into account the fact that the neutrons vary within our isotopes, okay? So all of these are carbon, And you can look on the periodic table and find that carbon has an atomic number of 6. We could also look in the pictures and we could count the protons, okay? In this case, these are carbon atoms. We don't see charges anywhere. They don't tell us that they're ions. So remember that the protons, if they're atoms, the protons and the electrons are going to be the same. And then to find the neutrons, we need to take the mass numbers, which those are designated here. You can see there's a couple of different ways you can see them written. Sometimes it's just with the symbol and sometimes it's with the actual name. So they're all carbons, they're just different isotopes of carbon. And so to get the neutron number, we simply take the atomic number, which was 6. That's going to be the same all the way around. And we're going to subtract. So 12 minus 6, 13 minus 6, and 14 minus 6. And that's going to give us our answers, okay? So just be sure you know that the same material that we've already covered, the protons, the neutrons, and the electrons, the only thing we're dealing with isotopes is that the neutrons can vary from atom to atom. All right, now sometimes these isotopes, these particular atoms, the nucleus is not very stable. And so what will happen is, in order to get to a more stable state, the nucleus will just give off particles. It may give off an alpha particle, a beta particle, or a gamma ray. And these are what we call radioactive isotopes, or sometimes you'll see them referred to as radioisotopes. And essentially when they give off those particles, what they're doing is they're emitting radiation. And so radiation is just something that can be detected. It can be harmful, but we can also kind of use it to our benefit. And we've already talked about different imaging techniques. This is the type of thing that we're using in a PET scan. We can also use them in medicine for a variety of reasons. And so radioactive isotopes are just used because we can kind of trace and track and detect the radiation that they give off. So this is just a few examples of some radioisotopes. These are some that are used in the PET scans. Remember, a lot of times they give off gamma rays, and then they can use those to create those images. And then over here we have some different functions in medicine. If you know of anyone who's been through radiation treatment, this can be used to treat cancer cells. Now, radiation is not good for our cells. So we don't just want to blast our whole bodies with radiation, because that could actually cause cancer. So what they do is they specifically target cancer cells and try to disrupt them and get them to essentially die. We can also use them as tracers. And so a lot of these, as you read through their functions, they kind of trace different pathways. So here it says a radio tracer. Because they can be detected, they can kind of be followed through the body and through organs, and it allows them to kind of see, where the elements are going, maybe where they're collecting, the pathways that they're traveling in, and so a lot of times we just simply call them tracers. All right, so when an atom has an unstable nucleus, it is called, all right, we actually haven't talked about electrolytes yet. We're going to be talking about those soon. We have an anion, which is a negative ion, and we have an enzyme, which we have talked about a little tiny bit. Enzymes are proteins, and so the best answer here is radioisotope. All right, and that's where we're going to stop for that video.